It's a real pleasure to be here. First time at the retreat, long-time viewer on video. It's fun to be among so many of you who are also working on equitable decarbonization of buildings. A lot of us working on that electrification problem. And what do we want? We're wanting low rates, low capital costs, low metals consumption in these projects, because we know that there are finite resources in the world. We're wanting a good match of the workload to the workforce so that we can get good project prices. So those are things we're wanting. And so my MO has always been, I work with kind of moderate ideas and magnificent partners. So I try to figure out who to work with to try to push a little bit of change through. And so today I'm going to have you take a little journey with me, looking down from the weeds a bit. We'll get into some real details and we'll look up towards the clouds. But I want to try to get you to get us both to share some ideas, questions, hopes, dreams, maybe some requests of what we want done. And next, I've got a lot of slides that'll be blowing through. Oh, actually, I should back up one to mention. A lot of this is coming through work I'm doing with Jill Gray-Ferguson, a Stanford PhD student who's looking to do some modeling of what will it take to, or what are the benefits of moving towards more power-efficient design policy. Power-efficient design is just another name for the Watt diet, and so I'll be using that name. Next. So this graph shows some California housing transition goals. Up to 14 million homes transitioned by 2045 from being mixed fuel homes to being all electric homes. You see a plot going along there. This little dotted line down here at the bottom shows about how many we can afford to do with all the massive IRA funding coming in. So it kind of gets exhausted probably by this time next year, if the rates of adoption take off. But then that little dot there is showing when the IRA tax credits run out. And so then we continue on trying to continue a massive electrification effort without those two incentives, hoping more incentives come along behind, or that things get cheaper, or that rates realign. Next. Okay, power efficient design, or PED. It's also the Watt diet, but it's basically getting people's end use needs met. What do we want? Hot shower and cold beer. Okay, but we also want thermal comfort, cooked food, dry, clean clothes, and mobility. So we want our miles met. So we want those needs met well. And to do that, what power efficient design is doing is using design practices to get right-sized equipment and the most efficient equipment and harvesting the savings from that, recognizing it in the electric panel and using that permission to get more and more electrification done on the same electric panel and on the same transformer in the neighborhood. So we've got neighborhood transformers up on the pole and they're serving 1 to 10 or 12 houses. And we're seeing in some places that a few customers put in a few oversized car chargers because they didn't know any better and they wanted to play Indy 500 at home, and their electrician told them a 50 amp charger was what they needed. They put in those chargers that are good enough to give them about 109,000 miles a year of charging if they only charged 1/3 of the hours of the year. So they could get 300,000 miles of charging done if they have their cars take turns. Most of them drive 10 or 15,000 miles, but they're getting these chargers that can do 10 to 30 times what they're driving. Okay, so what the power efficient design is doing is it's freeing up the workforce also. If we're able to do this power efficient design, you need fewer electricians upsizing panels, and so then those electricians are available to be putting in the needed circuits where they're needed and doing the needed upsizing of 30 amp services or 60 amp services up towards 100 amps to really meet the large North American lifestyles. Next. Okay, so this is one of my favorite charts. It's nice and boring, but it's showing the 5 basic end uses of drying clothes, cooking food, heating water, HVAC, and electric vehicles, and just showing by the length of the blue bar, which in this case is watts, counted on the, I think it's watts counted on the electric transformer or the panel, by several different ways to meet those end use needs. The shorter the bar, the more power efficient it is. And the longer the bar, the more power intense or power hog pardon the pejorative, I really enjoyed the pork today. But I use the term power hog to describe how we're kind of doing a lot of electrification now, and power efficient is how I hope we'll do it. But what you can see is there's a wide variety of how power intense you can get your end use needs met. And that's basically, for the car charger example, having this charger that people are using for a couple hours a week versus this other one, say a 120 volt plug-in to the regular socket that they might be using for 6 or 8 hours each night. And they both can be giving them the 13 or 15,000 miles that they're actually driving, but one of them takes up a lot of space on their own panel and on the transformer that their neighbors could have used to electrify. Okay, so this is just a different view of that whole power efficient design graph, just taking the 4 end uses, putting them in the corners, and having the remaining amps available shown in the middle for EV charging. And so like with space heat, they could use a right-sized inverter-driven heat pump, or they could use a regular oversized single or double speed heat pump with a resistor strip. And that would take up more amps or watts and consume space that they could have used for other things. And so I'm just showing that with water heaters at a 120 volt water heater, or 15 amp 240 volt, or the very common 30 amp 240 volt. Doing the same thing over there with drying. My new favorite device is the heat pump version of the combo washer dryer. 2 hours, you put dry clean clothes or dry dirty clothes in, you get dry clean clothes out 2 hours later. Really neat. You don't have to work in between. Or people who like to have 2 machines can have a heat pump dryer or a resistance dryer. Those consume more space. Next. Okay, so the thesis that Jill's working on in her PhD is that power efficient design can lead to a greater equity in what we're pursuing by expanding equitable access, by decreasing the ongoing and upfront cost of electrification, encouraging and empowering more DIY solutions, and then also can defer grid capacity expansions by leaving that transformer space, and that can help keep rates down, and that can help us speed up the adoption of electrification. I'm afraid we're going to run into a rate jam on the power poles if we aren't doing that. And then smooth the workforce ramp up. At those rates I was talking about, the electrification rates we're needed to do, we don't have nearly the workforce. So we need to figure out how to do the same work with less hours per home. Next. So one thing I propose, I used to have a pretty neutral approach to how to do electrification planning. I'm trying to go towards now a power efficient approach, which is start the client down at the very highest efficiency equipment and the right size, and not start them in neutral. Start them at the power efficient end of the equation, show them how much space is remaining on the panel, and asking if they want to go more opulent in one of these 5 end uses to consume some of that space, take it away from their car charger. But start them at the most efficient side of the equation, and then let them lobby to go consume their neighbor's ability to electrify and consume their grandchildren's ability to have a safe climate. So start them where they ought to be and let them beg to ruin the future. Next. So we've got our power efficient design versus power hog columns for meeting these different end use needs. And so we'll define those sets. And then we're looking at a very nice Redwood Energy diagram that came out about who owns what part of the equipment and what kind of upsizing we have to do based on different portfolios picked, and how many houses does it take before we have to upsize the transformer. How many transformer upsizes does it take before we have to upsize this feeder wire, this 4-mile long feeder wire, going to a transformer at a substation that has to be upsized. And you saw pictures yesterday of those big transformers on the Hoopa station. And then with that, do they even need a new substation? And maybe that's not a problem at the Hoopa substation. Maybe they've got room, but in a lot of our cities, they don't have room.
They have bigger problems. They don't need more problems from us.
Next. All right. So distribution rates in a utility, they are the system costs divided by the kilowatt hours sold. So we're going to model that. We look at the book value of legacy assets and the book value of new assets needed to meet this electrification. With less upsizing needed. We can save on the amount of new assets needed. That can help keep the rates down. So we'll just build that into the model. Next. And so rates will be lowest if we can keep the labor costs and the hardware costs low, and if we can increase the kilowatt hour sales quickly. The faster we can get more sales through the utility system, the more we can lower rates. Next. So contractor and labor have a tendency that economists call rent seeking, which is when there are shortages of things, they use their prices they charge as a way to ration out the available labor they have. So a contractor who's really busy, you ask him for a bid, you get a high bid. You've got to outbid all his other opportunities and outbid his vacation. Okay, so that's rent seeking, which is just the seeking of unusually large profits. Compared to if there were lots of contractors and he didn't have as much work on his plate because it was distributed across lots of the workforce, he wouldn't have to price himself up there because he's got available time that he can bid out at a normal rate. So we'll try to model rent seeking. Next. A little example of rent seeking. There's this little diagram in demand for more contractor hours per home going across this way. So complex electrification, simple electrification. Sort of the power efficient design and 120 volt devices down here. So cost of materials and labor, then he's got a normal profit, but the higher demand goes, the more rent seeking he has to do to get his demand down to meet his supply of labor. Next. All right, so we're going to build a big model. This is the top edge, PED versus HOG policies. Again, PED is power efficient design and HOG is regular power hog. These are the variables we'll be looking at. I'll just describe a few. This is panel size, service line size, branch wire in a house, appliance equipment, and then the electricity. Then also we'll be looking at contractor hours in the home, the utility worker hours to do all the upsizing they're doing on the poles, in the transformers, and then the electrician work hours. Next. So we'll also be looking at our objective function is how long will it take to meet those state goals. And so we'll be building that out. We'll be looking at a basic stock and flow diagram. And next. We'll be filling it in with installs per year of labor that people have available and a participant upfront cost model. So trying to get both those going. Next. So we'll be building in operating cost models for that life cycle cost analysis. And we'll be building in the utility distribution model for what's going on when you've got 10 homes on a transformer and 3 of them go power hog. What happens next? And what if 4 of them went power hog? Can we go back to the diagram? And so we'll be building out that physical model. And so we just bring it all together and it'll tell us like about how many homes can you achieve per year, about where your rates will go, how much uptake there will be by the customers given those high project rates and high electric rates, and will that all stall out? Okay, next. So the analysis ideas is we'll start with 2,000 homes and 1 substation. That'll be our system, and we'll just, that substation has 2,000 homes, 200 transformers, 5 feeder circuits, 1 substation, and we'll start by trying 10 homes per transformer on hog. We'll watch the system bog down, and we'll report out that, and then we'll try 1 PED and 9 hogs, 2 PEDs and 8 hogs, and we'll just keep seeing where do we get relief, and then can we make something that even teaches policymakers how to deal with this? Next. Okay, so it's based on thinking about how the future is going to really unfold from about now through who knows when, 2045. This is a super optimistic view of what if we converted a lot of mixed fuel homes down here in this swath, swath 1, to the next swaths. We've got policies right now that are going towards power hogs policies. They provide money to upsize your panel. They don't differentiate between the power efficiency of different equipment, so you get the same incentive if you go hog or if you don't. Some of them don't allow 120 volt incentives, or don't allow DIY incentives. All right, then there's my favorite swath, number 3, right-sized panel and equipment, so power efficient stuff. Next favorite, right-sized stuff with automatic in-the-house controls. So things that do circuit sharing, et cetera, or circuit pausing. And then PG&E let out their big R&D RFP, and their big dream was people love them so much, they want to turn over control of the things in their house to the utility, and that they'll control it, and that'll fit better on the grid. And so what I want to do is try to buy them the time to win over all those big fans that, that they're expecting. So anyway, when you look at this view, you can kind of tell I'm expecting there to be a mix of all different solutions, and we're basically got things that'll jam us up here in swath 2, and several solutions that'll get us past that, and that right now all our policies are putting people into this danger zone. We're headed for a kind of a traffic jam on the pole top. Next. All right, so parts of the analysis we hope to do are kind of a catalyst approach, or what would you do if this uncertainty unfolds? How is your plan flexible? So we've got a table of that. But here's requests. We'll be trying to make some future insights. This is a new field, looking at power efficient design, kind of something that Redwood Energy has really helped popularize. And then what we need are more researchers, more PhD students, electrical engineers, et cetera, working on this and starting to resolve what are the issues. And this one research project I'm working on now won't resolve that many of them. So we're going to need more folks looking at it. So I want you to all start thinking, what do you want to do in this area? And do you know people who might be able to help? Next. All right, so what do we have? We've got some cost data that we'll be using in this analysis from RS Means, and they've got estimates of the number of hours it takes to do projects, so we'll be using that for our timing studies. We've got engineering guidance, the National Electric Code, et cetera. Data we need are worker hours per home to do different job types in the electrification. And we'll need some equations on that rent-seeking impact. When demand gets tight and you've got incentives pulling the price up, how high do contractors raise the price to get that balance? We see in the Bay Area, $8,000 water heaters. Yeah. So anyway, I just wonder how high it'll go. Next. All right, the strategic goal is to get program designers, and you guys may know them or be them, but get federal, state, regional, utility, CCA, county, and city designers of programs to encourage and require power efficient design so more customers can electrify on the existing infrastructure, and we need to double workforces. Doubling workforces won't be enough to pursue power hog. I don't know how PG could manage the workforce size they'll need just on the pole tops. I don't see how well they manage the ones they have. So, I can't imagine them with 5 to 10 times that workforce. It doesn't look good to me. So, power efficient design allows lower electric rates. And so that's another thing we're hoping, and that's going to help get towards a beneficial spiral, because we're kind of jamming up into the diminishing spiral. And then PED relieves some of the contractor workforce pressure that leads to that excessive pricing I've mentioned. So we also are not saying that you don't upsize the distribution system. It's just that on the power hog thing, I think you have to upsize it 3 times. So you go through a wave of upsizing, and then another 1/3 of your customers electrify, and you go through another wave. And they're not looking forward. The policies that utilities use are that they're not allowed to do so much investment that the assets they're putting in aren't deemed used and useful right away. So that shrinks how far they go. But we know this all has to grow so fast, and then so that makes them go back again and redo it. And that ramping up each time to do it again is just going to add to cost. Next, which I think might be the last. Pragmatic advice. If anyone's designing programs, please end upsizing incentives for panels that exceed 100 amps. Let the hogs pay for their own damn panel. You don't have to use public money to oversize their systems. Okay? Start PED incentives. For example, the Golden State rebates for water heaters covered only 240 volt, 30 amp water heaters. They did not cover any power efficient water heaters, not the 15 amp 240s, not the 120 volts. Okay, offer heat pump incentives only up to the first 2 tons and not available if they're going to use resistance backup. So then if you want an extra ton, yeah, pay for it yourself. So we're not outlawing it. I'm not cruel, but just use the public's money to get the public's interest pursued. Offer incentives for combo washer dryer machines. Has anyone seen an incentive for this combo washer dryer that saves a whole circuit and can be put in by the homeowner themselves? Doesn't even have a vent. There's no incentive for that thing, but it is the fastest way to electrify drying and free up the circuit for a car charger or something else. Offer incentives for 20 amp circuit controlled EV or controlled EV incentives. Quit offering incentives for 50 amp ones. If they want it to play Indy 500, they can use their own pocketbook. Start DIY incentives. We've seen some from Peninsula Clean Energy, but more folks need to start those. The federal incentives, the tax credits apply to DIY, but not, I haven't seen how the IRA upfront do. But move other incentives up to the distributor level and the store level, so they're available automatically. Like in Oregon, when I go to the counter to buy my daughter's water heater, it's a heat pump water heater and the price is only $800. When I go to Lowe's here, it's $2,200. And then there's paperwork, if I think I can find the paperwork and fill it out and trust myself enough, but anyway. Let's see. So quickly phase out the hog incentives we have on equipment, and then lower the rate of return that is being allowed on distribution upsizing to the utilities. It's now at, I think, 11%, but lower it to something else. This is not risky assets. They don't need huge returns to put them in. I think that's my last slide. Woo! And, hey, a question. Greg.
Yeah, so let's assume we do all that stuff in terms of incentives, rebates, structures, and all that. How do we get contractors to stop oversizing heat pumps for space heating? How do we get them to stop installing 200 water heaters for 2 elderly people? They just have a huge incentive to just go bananas.
Yeah.
Electricians too, right?
Yep. Thanks for raising that. So a lot of us have been in energy efficiency a long time, and we've heard the term the split incentive problem. And we've often used that related to landlords and tenants, how one pays the bill and the other one has to pay for the equipment. There's a really big split incentive problem that Greg's just outlined. It's between the trades and society and the owner. The trades have multiple incentives to raise the size of the equipment they put in and add more bells and whistles that protect them. Like their basic great example is oversizing the heat pump in order for them to be sure they won't get a call on some cold day. They not only make more money oversizing it, they also think they're decreasing their risk, and they're decreasing the occupants' comfort some by having the system now that's kind of not getting in control. Its deadband is now too high, and so the thing has to cycle off in a lot of our moderate weather, and it actually produces more discomfort, but not so much that they call the contractor. And so they learned to live with it, but the contractor pocketed all the money from it, and society had to bear all the expense of upsizing for it. So we've got these split incentives. As program designers, we need to get ourselves thinking about what those are and designing them out. And so that's why my little simple example was incentives up to 2 tons, and not for the 3rd ton on that system, but we'll still give you an incentive on the first 2, and then try to make all that transparent to customers.
Make them do a manual jet.
or compare to therm use, but yes.
So I don't think you mentioned permitting in your kind of design of things to look at. Often, the more complex projects, a whole lot more permitting and inspections. That's a big incentive for contractors to push costs way up. So are you looking at that?
I hadn't thought of building it into that model, but one of the places it'll kind of, that it shows up in real life is that combo washer dryer. You don't need a permit for it. The funny thing is, a 120 volt water heater, heat pump water heater, has all the same connections as a washing machine, and you don't need a permit to change your washing machine. It's got a hot water line, cold water line, a 120 volt plug, and a drain line. Those are all the same things a 120 volt heat pump water heater needs. So I have another movement I'd like to start called decriminalize water heating. And it's that no permit needed on 120 volt water heaters.
Can you expand more on the 7% versus 11%?
Okay, and so I think I saw Dave was mentioning 10% yesterday. I hear 11, I don't research much, so it's one or the other or in between. But the utilities are, the way they make money is not by selling volume. They do not make money selling more kilowatt hours. They make money being allowed to earn that 11% rate of return on expanding their system with more poles and longer wires, or on upsizing the size of the wire, or using a more expensive conductor. But any capital investment they're making goes into what's called book value. So we'll put that economic model into the model. It's the book value of their assets, and they're depreciating over time. They have a time scheduled depreciation that they're allowed to also charge. But they charge the rate of return on the book value, and then each year the book value steps down for that one asset. They charge that as an expense to the customer. They collect both those numbers in the rates. The rates are determined simply, the rates aren't a goal. The rates are just the result of saying, what is the allowed return by the utility divided by the estimated sales? That's the rates for next year. If we overestimated them and we collect too much money, we'll give some back by not charging as much the next year. If we undercollected them and we don't have enough, we are allowed to charge more next year. So they do a balancing account. But the way utilities make money in a decoupled regulatory system, which we decoupled in order to pursue energy efficiency, decreasing sales, the way they make their money is on the book value of their assets.
You're saying that they don't have high risks. That's why we could, if we had legislation to push it down to 7%. Can you expand on that?
Okay, so I look at it as copper wire. What are the chances something's going to go wrong with a new technology like copper wire? Low. The thing they got massive returns on was digging ditches to bury lines. What are the chances that something's going to go wrong with your ditch? So they're allowed to build assets that are low risk. It's not like a new G-Wizium battery system that might go funky. It's because we've never tried G-Wizium before in batteries. And so they're just doing the same old stuff at a bigger scale and earning kind of risk-based returns when there's no risk. And so I'm thinking they do not need to be allotted these high rates of return. So what if their stock price isn't as high? They shouldn't need to raise as much money. We'll show them how power efficient design keeps them having to raise the money.
That's not fair in the long term. In the short term, with the captured PUC that we have, that is true. There's no risk for them. But in the long term, and I've seen it in the past, where they have not been allowed to collect on a number of their expenses. They put these things down as costs, and the PUC said, no, we're not going to count those. So there is a risk when the PUC is not captured. Right now, it is.
Right, but they need to get approval to make these investments. I contend. I thought that's the system. They don't make them before they've got the approval. But if they made them before the approval, then they're at risk to get the approval.
All right, and with that, we're going to hold.
All right, thank you.